Okay, we'll just wait a few seconds here and let a few extra attendees join. So, all right. Hello, everyone. Thanks for joining our North American JMAG conference. My name is Brian Kowalczyk. I'm the JMAG coordinator for University Support at PowerSys. Today, we're privileged to have as our next speaker, Ho Yin David Wong. David comes to us from Portland State University, Oregon. He received his bachelor's degree in electrical engineering from Syracuse University, New York in 2015, and his master's degree in power engineering from Portland State in 2017. He is currently pursuing his PhD degree at Portland State. His interests are in the area of design and analysis of electric machines, adjustable speed permanent magnet drives for renewable energy, and electric aircraft. Today he will be presenting his work on using JMAG to design a Halbach magnetic gear. During the presentation, attendees can submit questions through the Q&A in Zoom or on the Whova platform under session Q&A. And as time permits, we'll answer some questions at the conclusion. So with that, I would like to welcome David. Hey, David.
Hi, okay. Thank you everyone for joining today. I'm David from Portland State University. This presentation, again, we'll be using JMAG to design a high torque density Halbach Rotor coaxial magnetic gear. A magnetic gear is a contactless alternative to traditional mechanical gearbox. Mechanical gearbox usually operates loudly and would require routine surfaces for lubrication due to the wear from the contacting gear teeth. Therefore, if properly designed, with the contactless property of a magnetic gearbox, it has the potential to eliminate most of the problems associated with mechanical gears. And in addition, it is able to offer the capability of increasing power conversion efficiency and inherent overload protection. Also, if a highly competitive torque density is achieved, magnetic gear should be able to replace mechanical gearbox in the future. This research is to design a magnetic gearbox with certain design objectives. First, is to achieve a high volumetric torque density, perfectly about 300 Newton meter per liter, while remaining a small outer diameter, where this small outer diameter is optimal for wind turbine application. The assembly procedure for magnetic gearbox has always been a struggle. So for this design, we have the intention of improving the assembly process and hope to benefit future designs. Previously, a main source of loss was due to the conductive material we use for cage lamination support. So if we want to improve losses on this design, we will need to make some modification to the cage modulator. In order to accomplish all the tasks, some decisions were made at the very beginning. Halbach area was known for its property of creating highly sinusoidal field distribution, which offers the potential for both increasing torque density and lowering harmonic related loss. Therefore, Halbach area rotors were applied to all magnet rotors for this design. An OD of 120 millimeter was selected for its size limit. And throughout the design process, we would need to ensure that all final geometric parameters are feasible to fabricate. And the assembly procedure should be considered while making all decisions. Finally, cage modulator segment design will be modified to have a non-conductive material support structure. To begin the design process, few parameters were fixed. The pole pair combination was selected with 2 prime numbers to begin with. Ideally, with prime numbers selected, the design would result with a lower torque ripple Therefore, P1 of 3 pole pair, N2 of 17 pole pairs, and P3 of 14 pole pairs were selected to each rotor. This gear ratio was selected since it is within the most suitable range of gear ratio for small-scale wind turbine application. And similar to the use of Halbach array, in order to maximize torque performance of the gearbox, air gaps between rotors were set to the minimal mechanical fabrication limits of 0.5 millimeters. In terms of material, N48 neodymium magnets were selected for torque improvement purposes, and the cage rotor will be laminated steel in order to lower eddy current losses as much as possible. With all the decisions made on these fixed parameters, 3 main variables were swept: the inner radius of the inner rotor, RI1, outer radius of inner rotor, RO1, as well as the cage rotor radial length, L2. Any other parameters would change accordingly to these 3 variables. A total of 2,244 cases were simulated under JMAG's 2D FEA static analysis when the gearbox is at peak torque angle. Volumetric and mass torque density were calculated to generate this plot. The color-coded legend indicates data points with different cage rotor radial length, where the top right boundary region of the plot would be most notable design to look into. So here's a zoomed in image. We can clearly see the performance of each interested cases. The maximum mass torque density and maximum volumetric torque density cases were easily located, where the maximum mass torque density is labeled as design A and maximum volumetric torque density is labeled as design B. They are showing about 17 Nm per kilogram and close to 400 Nm per liter respectively. However, we decided to not carry on with any of these 2 designs due to the fact that some dimensions were not feasible to turn into an actual prototype. For example, cage rotor radial length for both designs are so short that it's less than 10 millimeters. Any supporting structure we would use might deflect and close up the air gap. Also, design B requires a inner rotor inner radius of 8 millimeters, which was not preferred since we would like to have shaft going all the way through the inner rotor. To make the design mechanically rigid, we considered few additional limitations on the geometric parameters. L2 and RI1 were limited to be no smaller than 10 millimeters and 15 millimeters respectively. And under this assumption, the trade-off design C was selected. Design C would have a relatively high mass torque density and volumetric torque density, while mechanically it would be feasible to fabricate and the structure should be rigid. In addition to the aforementioned geometric parameters constraints, furthermore considerations and modifications were made based on the trade-off design. As mentioned before, we would modify the cage design to allow a non-conductive material to further reduce losses. Where you can see here, for the cage rotor, the slot has been made with a rectangular slot in order to fit the supporting structure, as well as the inner rotor and outer rotor design. They now have back irons for each simple assembly purposes. So in order to make the assembly easier, we now have back irons for both inner and outer rotors. With the magnets wanted to attract to the ferromagnetic back iron naturally, the assembly would be easier. For inner rotors, since a shaft would need to go all the way through the rotor, the back iron was determined to be a solid cylinder with radius of RI1. However, the outer rotor back iron still remains undetermined. With the full axial length of the active region covered, the radial thickness was swapped to study the performance. Outer rotor back iron thickness LB was added beyond the active region OD of 120 mm. As expected, outer rotor back iron with outer rotor back iron implement, the torque reduced. LB of 3 mm was selected for a higher torque as it was the minimum thickness required to provide sufficient mechanical strength. It can be noted that when only inner rotor back iron was implemented, the torque performance was not affected negatively at all. Axial length of the model was also studied for its impact on torque performance. Finalized 2D design was extruded to different axial lengths. 2D FEA simulation torque result is changing proportionally to the axial length. However, the 3D finite element analysis simulation showed a nonlinear relationship between the model axial length and the torque density performance, which was due to the axial flux leakage as known as an effect. If mechanically feasible, a long axial length would be optimal. A long axial length would optimize the torque density performance of a mechanical gearbox. However, according to deflection analysis from the mechanical study, we finalized on an active region axial length of 50 mm. So cage modulators are now modified to have rectangular slots. These slots were designed for the insert of garolite bar cage support. Garolite is a non-magnetic, non-conductive material. Therefore, comparing to previous designs which had steel rods going all the way through the center of cage segments, losses should be reduced. According from Gerber in 2014, they showed that if cage rotor axial length was reduced slightly, the torque density could be improved, which leads to this last sweep analysis on cage rotor axial length, BC. With a final active region stack length of 50 mm, the torque peaks when the cage rotor is 47.5 mm long, where the torque increased slightly above 1.3%. Here's an image of the final gearbox design showing all the modifications that were made. After confirming all the geometric parameters, 3D FEA simulations were conducted. First, both inner and outer rotor were fixed with only cage rotor rotation, which is the case of pole-slipping. And the final achievable peak torque was estimated to be 160.6 mm, which is 284 Nm per liter. Second, 2 rotations were applied to inner rotor and cage rotor according to gear ratio when the gearbox is at peak torque angle. Eddy current was allowed, and such demonstrate the torque ripple of 0.58% at peak torque. Here's a mixed contour plot of the flux density, where BR, B theta, and total flux density are shown. From the image, we can see that the cage bridges were all saturated. These 2 images demonstrates the 3D model from JMAG and showing the vector plots for magnetic flux density, indicating the direction of the flux flow. And here shows the flux modulation effect, which is one of the main concepts behind magnetic gearbox. With the outer rotor removed, the radial field was measured in the middle of outer air gap. When only inner rotor was present, we can see a perfectly sinusoidal plot, which is the outcome of the Halbach area magnetic arrangement. Then cage modulator was introduced back to the system, and the field was shown to be modulated. From the harmonic graph, we can see that the 14th harmonic from P3 of 14 pole pairs was present even when the outer rotor was removed. And that validates the modulation effect. After all analysis on the design, it was time to build a prototype. All Garolite bars were inserted to the slots on cage lamination, and Halbach area magnets are placed on both inner and outer rotors. The installation of magnets was indeed easier with the help of ferromagnetic backline. Radial flux density was measured on both inner and outer magnet rotors to study any discrepancy between FEA calculated result and experimental result. Flux density was measured with a Gauss meter on both the assembled rotor isolated from all other components. After collecting all data, a harmonic analysis was conducted. Here we can see the result for inner rotor. It was shown that the inner rotor Halbach area magnets are slightly stronger than expected performance from FEA. And now we can see the results for the outer rotor. It was shown that the outer rotor Halbach area magnets are slightly weaker than expected performance from FEA. After the experimental measurement of the rotor field, all rotors are in place and the prototype was fully assembled. And here's some image of the gearbox. The peak torque was then measured experimentally. This plot is showing the static post-slipping torque. The experimental torque was measured to be 147.8 Nm, which is about 8% lower than 3D FEA calculated values. The associated torque density was 261.4 Nm per liter. The prototype was later placed on the test bed with motors and transducer to measure the torque and torque ripple with 2 rotation constant torque condition. Where cage rotor input DC motor was in torque control mode and permanent magnet motors on inner rotor output side was in speed control mode. Here shows the measurement on the constant torque result. Inner rotor was controlled to be running constantly at 300 RPM, and torque was applied to cage rotor with 55 Nm and 105 Nm. We can see that even though the torque was successfully measured, the torque ripple was significantly higher than expected. We then suspect the additional ripple was from the testbed setup or other unexpected mechanical issue. After carefully studying the setup, we noticed that the components were not aligned properly, where couplings was even damaged due to the misalignment. So here shows a summary for the final prototype performance. Can be noted that as a proof of concept, the mechanical structure designed for the prototype was imperfect, causing the full assembly to be bulky and heavy. Hence, the full assembly performance is less impressive. So to continue study on this prototype, we will need to align the setup properly and study the noise from the testbed. After doing so, we are planning to create an efficiency map on this gearbox by measuring the loss at multiple torque level and multiple speed. Again, I would like to thank you, JMAG, for the use of the FEA software. Thank you. If there's any question.
Hey, David, nice job.
Yeah, thanks.
Thanks for that insightful presentation on the Halbach magnetic gear. Thank you. So anybody feel free to put your questions, submit them on the Q&A at the bottom of the Zoom screen, or also in the Whova app. So we'll just, we have a few minutes for Q&A, so feel free to put your questions in. Thank you. We'll just hold on here, David, for a few minutes.
Okay.
So here's a question coming in, David, and on Huva.
Okay.
So will the power supply be DC or AC? If AC, how many phases power supply are you expecting to use with this project? How about the phases of the traction motor?
Um,
And would like me to repeat that for you?
it should be, it's okay. But let me show.
Oh, sure.
Yeah, so, well, we're only simply testing the gearbox. I mean, if you are determined to be the motors that have been used for this experimental setup, there's a DC motor and I think it's three-phase, it's DC as well. Yeah, but I have a video actually. Maybe it will run. Yeah, so that kind of shows the result. Like, I don't know if it answered the question, but
There's it's like another question here on Huva. Were the eddy current losses considered on the magnets?
yeah.
Okay, so
Yes.
that's all included in your results then, right?
Yep. Yeah, those were set to be allowed under JMAG.
Okay, thank you.
Oh, okay.
Let's see. There's a Q&A. I apologize. I'm running back and forth here from Peter. On your simulation work, could you comment on any challenges you faced in mesh discretization?
Well, I would say, well, first, JMAG allows you to control the mesh very, very well. So we are able to set up the mesh condition to a point that which kind of already max out our computer performance, which we do have nice computers. So I don't think, not really, like we are able to maximize the number of elements we have during any simulations we make.
Okay. So let's see if we have any other questions here. Yeah, I'm not seeing any other questions coming in right now. So, so with that, I'd like to again thank David.
Okay.
We really appreciate your time and your nice presentation. And so I would ask that if anyone has any other questions, maybe feel free to place those on the Huva app, and or you could maybe or you could attendees can also look up David and you could converse on the Huva app and kind of have maybe some other discussions yet today.
Yeah, so, sure, I will.
Okay. So appreciate, David, if you do have any other questions, maybe you can take a look at those online.
Yeah, sure. I will keep an eye on that.
Thank you so much. With that, I think we'll close this session. And just to let everybody know that there's another university presentation coming up here just shortly in another minute or two on wireless fast charging applications. So you can join that next session here once you leave this one. So that'll be it. David, thanks again, and we'll end this right now.
Thank you.
Thanks, everyone.
Thanks.
Okay, bye.
Thank you.